So this is the dongle, and I can just plug it into the scope. It'll make a sound, and the scope app will crash. Very cool. Hello engineers of YouTube, I just wanted to give you guys a quick little overview of this Micsig STO1004 oscilloscope that recently came out. It, I guess, is their third generation of oscilloscopes based on this tablet form factor. The original one was basically just this, with a couple of soft keys on the side. Then they had a version with turnable knobs, and this version has joysticks which you can push, and you can also tilt them up, down, left, right, and that will give you quick access to commonly used basic controls. At the top we have the 4-channel inputs and an auxiliary output. This is not used for anything at the moment as far as I know. The user manual for the current oscilloscope doesn't even mention anything about it. However, I found a manual for an older scope where it says that the aux out is used to measure the waveform refresh rate of the oscilloscope and cascade the current oscilloscope signal to other oscilloscopes. In practice, when I hooked this up to another oscilloscope, I got a signal out of it which was at a frequency of tens of hertz, and so I'm not sure how to interpret that as far as correlating to the refresh of the oscilloscope, but that's what I got. As you can see by the pads that are present next to the input of each channel, these are smart inputs, and Micsig calls this their Micsig Universal Probe Interface, or UPI. And one of the probes that supports this is their new differential high voltage probe, the DP750, which you can simply hook onto any of these channels. It gives the probe the 5 volts that it needs to operate, and it automatically sets the attenuation ratio for the probe. So here's an example of a differential probe setup using Micsig's DP10007 probe, and it's currently measuring a signal from a variable frequency drive that has a peak-to-peak voltage of 660 volts. The 600 volts is coming from here and is going to a special junction box, but you can see, you know, all of these wires are kind of not fun to have around, and it makes measurement in the field a lot more difficult than it should be. This is actually quite a lot more convenient than using regular differential probes, which require you to connect the scope to USB, which is present on this. I'll show you that in a second. But you know, you end up with a lot of wires, and I think, you know, this is a much nicer way to work if you're probing high voltage signals from, let's say, variable frequency drives and such. You just, you know, hook the probe up on top, and you know, you can measure whatever you want. Looking at the back of the scope, there's silicone tape covering up my serial number. We have a fan, unfortunately. So the fan is kind of on the loud side. It's not super loud, but it's not super quiet either. So, you know, whether it will bother you or not in a lab is up to you. I thought it was alright. For me, you know, I didn't think it was much of a problem. A lot of my other equipment is much louder, so this is kind of, you know, relatively quiet. But if you really like your lab to be silent, oddly enough, this oscilloscope might not be, you know, great for you. However, the overall design of the scope is really good. It's got these extendable feet that you can pull out, and these supports that pull out underneath the feet. And this actually means that the oscilloscope is very stable, because, you know, you can push on these really hard and nothing will happen. So leaning it against a hard surface works very well. And to collapse these, you just kind of push them in, and that's it. Let's take a look at the battery. The internal battery has laptop-like contacts, which seem very robust. It's 7500 mAh, 7.4 volts. To fix the battery in place, we have 3 little tabs on the back of the battery, and we have 2 metal threaded inserts for the plastic. And so to install the battery, you just pop it in like this, and that should be connected. Looking at the side of the oscilloscope, we have a power button, which is clearly a soft button, which illuminates. And in order to prevent this button from being accidentally pushed in your backpack, etc., there is actually a hard switch here, which doesn't look like it's meant to carry very high current, so it's probably another soft switch that's just in series with a push button. We also have prongs for probe compensation and 2 USBs, including USB 3, HDMI, and USB-C. I'm not sure if you can charge this oscilloscope through USB-C though. And then we have the DC power jack for 12 volts. There are also 2 threaded holes for screws right here and right here, so I'm not sure if that's for some kind of a cover to give you some water resistance or for some weird accessory. And looking at the bottom of the oscilloscope, we have some air vents, and we have 2 sets of holes for what seem to be speakers. I'm not 100% sure. But because this is basically a tablet that's running Android 11 to be specific, maybe these are speakers and you can just, you know, make use of them playing videos and whatever you need. And on this other side, we just have a rubberized carry handle, which kind of allows you to handhold the scope, to be honest. It's kind of heavy, so I wouldn't really say that this would be a good idea, but you can probably use 2 hands to do this and that would be fine. Alright, so I got it set up here and let's see how long it takes to boot. The fan initially turns on, but it's very quiet. If you have the oscilloscope running for maybe like 5 minutes or so, then the fan will kind of turn on and stay on, and you can definitely hear it. I mean, my room is fairly loud here, got a lot of stuff going on, but it's not too bad. Just some people are very picky with that. Almost there. Alright, so that was about 38 seconds, which is kind of longer than average for sure. I've certainly got scopes that boot much faster than this, but you know, it's fine. The turn off time is much faster, so if you have to, you know, pack up and leave a work site quickly or something, I will show you how long that takes. So you hold the power button to get a menu and you can just press power off and it's off. So the power off is actually almost instant. For a little demo of the fan loudness, I will use my shotgun microphone and I'll point it at the oscilloscope so you can hear what that sounds like. It's a fan, it's not too loud, but it might be too loud if your lab is really quiet and you want the silence. Alright, so now I'll try to cover some general controls for what the scope works like. So there's a main menu, which is accessible by pulling down from the top, which is this menu here, and it's subdivided into these top categories right here, and then underneath each category you have subcategories. Does that make sense? So each item has quite a few things you can modify, and the very first thing is a measure menu, which has all your measurements. That's what these measurements here at the bottom are, and the yellow ones are for the first channel and the blue ones are for the second channel, so it's all color matched. And of course I can just go here and I can, you know, remove the second channel measurements just like that, or add, you know, if I select channel, let's say 3, right, and I want the rise time and the fall time for channel 3, then I can just do that and that's done. So it's actually very straightforward to add these. And if I wanted to add, let's say channel 4 on top of this, right, I can do that too, and it'll just appear separate like this. So it's 5 measurements per line, and they can be from pretty much any combination of channels, whatever you want. And this is actually a very nice way to work. There's also a built-in hardware counter, which is this right here. And you can select which channel you want it to take the measurement from, or you can just disable it if you don't want it. In terms of the basic time-based controls, it's this joystick right here that you would use to change that. So you can decrease the time base, increase the time base. And the maximum here, the highest resolution would be 2 nanoseconds per division, and the largest scale is 1 kiloseconds per division. And of course you have rolling mode as well, which engages, I think, at like 200 milliseconds basically. So past 200 you don't have it, but at 200 milliseconds per division you have standard rolling mode, so you can look for rolling events, which of course is very relevant to situations for when you're looking at slow changing signals. In practice it's very useful. Okay, so here's something funny. I have a lot of instruments in my lab, but I don't actually have a very high-end function generator. I have some really high frequency signal generators in the multi-gigahertz range, and I have some really, you know, junky, super low-end signal generators which don't really have very fast edges. For this demo, what I instead ended up doing is I wrote a little 160-line program on an FPGA development board which will generate a bunch of signals for me, and it will also generate some data that we can try decoding with the UART decoder that's built into the oscilloscope. So as you can see, these are 2 1 kilohertz signals, and they're actually coming from the same source on the GPIO outputs of the FPGA board. The signal integrity for these signals is all right. They're GPIO pins, and they're going through like TVS diodes for, you know, transient protection, etc. So, you know, they're not going to be incredible for high-speed stuff, but it'll be all right. The edges will be fast enough. And the channel 1 signal is coming through the Micsig probe that comes with the oscilloscope. Channel 2 is coming through much more expensive 500 megahertz made in Germany LaCroix probe. So I did this so we can kind of see what the Micsig probe is like in terms of performance compared to a much higher end probe. However, one of the things that stands out to me is the fact that the amplitude for these signals is kind of jumpy, right? It should be 3.3 volts pretty consistently, but it's not very stable. And there's no way to change this in the sense that some oscilloscopes have features that will average out the statistics over time. I don't think a feature like that exists here, but you can, for example, play with acquisition parameters right here. So if you go to sample and then mode, you can change the acquisition mode from normal to average to envelope to peak detect. So if we go average, we can set the number of averages up to 256 is the max. But even that, as you can see, doesn't really help any of these parameters get any better. Here's the problem, right? This is... what is this? 0 second rise time. It should have enough memory depth. So we're currently at 1.4, which is not the maximum. So let me set this back to normal, and I'll go to depth, and I can force it into a higher memory depth mode by selecting this. So right now it's at 35 meg points of sample memory, and that should be enough to look at the rise time of the signals, but we get nothing. Normally, if your sample time is insufficient to display a sharp enough, fast enough rise time, it'll just increase, right? You'll get a much higher rise time than what it should be. So I'm kind of weirded out that it's not actually detecting anything. And if we go to a smaller time base and we just zoom way in basically into the signal, right? Now we get a valid rise time out of the signal. And now you can actually start to see that the LaCroix probe is a little bit faster, as it should be, right? It's a 500 megahertz probe versus the 100 megahertz probe. So there's a mild difference that favors the LaCroix probe, but you know, this is a 100 megahertz oscilloscope. What do you want? And as we increase the time base, the rise time is still maintained, and then it goes to 0. When does it go to 0? Let's see. So pretty much right here, so something kind of shows up, but then it goes away. So right here, it's active at 10 microseconds per division. We get a rise time, and at 20 microseconds, rise time disappears. That's very strange, because we're at maximum memory depth, right? So very odd. So, you know, this oscilloscope has a couple of little things like that, some random bugs, some of which I'll show you later with serial decoding, etc. But, you know, overall, it's a very good product. Would you use it for mission critical measurements? Well, I don't know. You tell me. One of the cool asides I can kind of give you guys is that I'm actually pretty surprised how accurate this frequency happens to be. Not that the scope gives a really accurate readout, I mean that too, but also how this is being generated, because I'm using a 125 megahertz clock on the FPGA board, which is then fed into a PLL, which generates 200 and 300 megahertz clocks, which are then being divided down to whatever frequencies I need, in this case 1 kilohertz. And I'm just really surprised by the accuracy of this process. I really didn't expect the base clock to be so accurate, because normally as you're doing all these multiplying and divisions of the clocks, you're losing accuracy with each step, and yeah, it's actually quite good. So right now I have the oscilloscope set to automatic mode, and actually more than that, I have it set to auto ranging, which is a really cool feature on this particular oscilloscope, which allows you to always display the signal correctly continuously. It will optimize the time base and the vertical ranging of the scope to fit the signal onto your screen at all times, and you can specify exactly which of these parameters you want to be automatically set. So the way that I have it configured right now, if I change the frequency of the signal, the scope will automatically select a time base to fit it, which is really great. So if I double this frequency, look at that, right? Now we're at 10 kilohertz, and the scope just automatically scaled everything. So if you're kind of turned off by these joysticks and you are dreading the idea of, you know, pressing the time base buttons, you don't really have to. For a lot of signals that you could look at, you can just leave it on automatic mode, and it'll do everything for you, which is really good. So this is 10 kilohertz. So let's go to 100 kilohertz. Now we have a rise time. Probably because the time base got reduced, right? And so somehow, despite the fact that it has all of the sample memory to be able to record these longer waves, it can't calculate rise time for longer time base settings, which is really odd. But at any rate, we have a rise time now, and we can just keep going up in terms of signal. So this is 1 megahertz. And you're starting to see some ringing, etc., but it's just a GPIO output on the FPGA board, so there are limitations to what I can kind of do with that. So let's keep going. So now we can see, you know, the ugliness of this type of probing. So this is 10 megahertz, and we still have valid rise times. The amplitude is still all right. And you can look at all the wiggles which correspond to different impedance mismatches and reflections that are going on, which is kind of neat to see when you just toggle between frequencies like that. So this is 10 megahertz, this is 15 megahertz, and this is 50 megahertz. So with 50 megahertz, you can clearly see, and see now the auto ranging doesn't know what it's quite doing. So that's, you know, because I'm not touching anything, right? So with 50 megahertz, the bottom trace obviously looks a bit better, a bit more definition, you can see at the top, etc., and the rise time is a bit lower. So you do get a slightly higher quality signal with the 500 megahertz probe. Would you want to specifically use a 500 megahertz probe on this oscilloscope? No, not really. Like the built-in Micsig probes are perfectly fine. So just for fun, let's keep going. So this is 75 megahertz. The hardware counter is very accurate. The measurement is less so. It's quite twitchy. And here's 100 megahertz. So in this case, the hardware counter actually fails because I think it's reaching some kind of limit. I'm not sure how they're actually doing this hardware counting, but it's hitting some kind of limit because this is very exactly 100 megahertz, as you can see from the actual measurements. And of course, you know, the wave starts to look like a sine wave at this point because we don't have the bandwidth for this oscilloscope. But actually, yes and no, that's part of the reason, but also it's the limitation of this probing method. If you really wanted to have very sharp 100 megahertz, you know, signal with very sharp edges at 100 megahertz, the rise time would have to be considerably lower, which means that I would have to use a completely different method of sampling the signal, which I don't currently have. So actually don't blame the scope for the fact that this looks like a sine wave. A good chunk of it is just from the fact that I'm hitting the limits of what this development board can output through the GPIO pins. And just for fun, of course, here's 150 megahertz. So you can see the signals are quite a bit attenuated, and the bottom trace less so than the top trace. So this is very obviously a bandwidth limitation of the 100 megahertz probe as well. But both of them are, of course, attenuated because, you know, for the bottom trace we have no probing issues because the probe will pass this frequency just fine. But the oscilloscope itself, of course, is, you know, hitting its limit for the front end. But I think this is still really excellent performance, and hey, you can see something, which is pretty good for a 100 megahertz scope. And we're back to 1 kilohertz. So, helpful demo. You guys know what to expect. Is this a good channel? Then please subscribe. And now a super simple overview of the rest of the user interface. Okay, so we have main menu at the top, and you can see all the different options. I mean, I can go through them. So we have measurements, we have counter for the hardware counter, we have waveform saving, so you can select what you want to save on a local disk or on a USB disk that you plug in. You can name things, whatever you want, so very easy to name stuff, and click save to save that particular waveform, or you can instantly save it to a reference waveform. So you can click R1, let's say, and now this waveform, if I disable channel 1, now let's do this. Now we're looking at the reference waveform, right, which is just active right here, and I can disable it with the reference button. So if I have channel 2 enabled, this is the reference from channel 1, and here's channel 1, right? So it just acts as its own channel that you can enable, disable, so very easy to use. And you can have your 4 reference channels, and it's just one button. You just literally pull this down, press a single button, and you got it saved. So that's actually very convenient, not just saved, but saved and placed on the screen. And so that's very good. And of course, you know, if you select one of these formats and just click save, it'll save it to a file on the hard drive. Then you have various user settings. So I think this is just total configuration for the oscilloscope, which you can save as named presets, which I'm sure is very convenient for many production situations where you want the oscilloscope to be configured for different tasks. And of course you have picture, you can put a timestamp on the picture, you can invert it. I don't know why you'd want to do that, but you can. And so this is basically for the photo mode. So there's multiple ways to take pictures with this oscilloscope. So one way to take a picture is just by pressing this button right here, which will take a screenshot of the screen. If you click on this, this will go into the Android's edit mode where you can apply visual effects to the image, which I don't know why you would want this, but you could do that. You can press the back button to get back to the oscilloscope, but in general, so if I go to there's a dedicated home button, I should say, which is really, really important. It's right in the corner, so it's easy to get to. And then you can just click on gallery, and now I can access the picture that I just took, and I can do all the usual things, you know, zoom into stuff, multi-touch, etc. And if I had multiple pictures, I can swipe to go between them. Because this is a full Android tablet, right, I can switch between apps that I might have open, such as, you know, here's the user manual for this oscilloscope, right, and I can just switch back to the, which one is which. That's gallery, that's the oscilloscope app. So now I'm back in the oscilloscope app. And it's really nice and easy to do this, actually. I mean, if you've used an Android tablet before. Another way to capture images and data from this oscilloscope is to swipe up from the bottom, which brings up this menu right here. And you have a capture button. So this will do the same thing, where it will just capture a screenshot, same as pressing this button right here. But there's a third mode, which is this button right here. If you press this button, it will take a screenshot, but it will also save a waveform. So, and what I mean is, you can click on the reference button here, and then pull out the reference menu, click on the reference, and this is the waveform that just got saved. And that's part of that screenshot. And I can disable the reference channel. And so this button saves both a screenshot and a reference waveform. Now, or just, you know, digital form of the waveform. Where are these saved, you might ask? Well, if we click on the home button again, right, we go to gallery, and so here's the screenshot, right? So we have two screenshots here. So this is the screenshot. We can click back and back and back, and we can go to files. And if we go to files, basically it's in this folder right here. By default, you'll be in, I think, documents is where it places you by default. And so you have to click on the hamburger menu and then click on oscilloscope. And then within oscilloscope, it's the smart folder. Actually, I just noticed something. Ringtones? That's really funny. Does your oscilloscope have ringtones? So you click on the smart folder, and right here you have ref wave. So you go here, and this is the waveform. So if you wanted to delete some of these reference waveforms, or perhaps rename them, can you rename them? Let's see. Rename. Right, that works. And so you click OK. We can go back to the oscilloscope app, and let's see if that works. So if I go to the reference menu, and I'll select something, test, there you go. And does that push it onto the actual screen as test? Oops, I meant to do that. So not really, it just says R1. Yeah, I mean, it doesn't really... What I wish it did, right, which would make sense, is if you took the name of this file and you displayed it here instead of R1 or next to R1, because sometimes you might want to know what this reference actually represents, right? Or like, you know, maybe name it 50M for 50 megahertz or something, and whatever you're doing, right? Or the type of bus that you're trying to sample. So that would have been a nice feature. But anyhow, that's kind of how you navigate this whole thing. It's a little bit cumbersome. You can get used to it. Now, I did something just now, which you might have noticed, which is that I swiped vertically on the channel bar. So of course you can select your channels by just, you know, clicking on them like this. It's actually like you can't click on it again to just disable it, which is really interesting. You have to pull it out and then disable it this way. That's very cumbersome, so I prefer to just press the buttons. But if you swipe vertically on this bar, then you get the math operations, and that's where you have your, for example, like FFT stuff, advanced math, and, you know, various channel things that you might choose to do. So, and here are your FFT settings for different features, and I'll show you that a little bit later. Just as well, you have your serial 1 and serial 2 decoding, which I will actually show you next. Okay, so it's been a hot minute, and I had lunch, and I can now show you another feature. So we're back to the same 1 kilohertz square wave, and now if I press one button, we get data. And it actually auto-scales it correctly, because the auto mode is still on, and that's really cool. So I have 4 speeds for UART programmed into my little FPGA board. This is 500 kilobits per second. This is 1 megabit. This is 4 megabit. Auto scales, and this is 8 megabit. So 8 megabit and 1 megabit. 8 megabit. Oh, it's taking its time. There we go, auto scaled, and not 1 but 500 kilobit rather, half a megabit. So the auto scaling, you know, is super convenient, honestly. Like, you see, if you have a weird situation, you don't really know what signal you're looking at, what frequency it is, this is great. and it works pretty well most of the time. So I can now show you another feature, which is persistence. So if you go to display, persistence right here. Actually, what else is in display? Waveform, where you can specify vectors or dots, and you can specify your general intensity, graticule control, and persistence. So you can set it to auto, which will automatically choose, whatever averages it will use for this, and I guess it's changing its mind as to what parameter it should be using. Or you can have normal, where you specify your own value, which is like time, to emulate, I guess, phosphor-based oscilloscopes for how much delay you want. You have a clear button. So you can actually clear persistence. So if you've captured your event and you want to reset it, you can just press clear, which is kind of neat. And of course you have infinite persistence as well. So if I do that, and then I manually zoom into a waveform, let's zoom in actually even further. So I'll go here, and now I can show you cursors. So you have two types of cursors, and they have dedicated buttons, which is really cool. You have horizontal cursors, and you have vertical cursors. So for vertical ones, which is what I want, you can drag them around, just like this, but if you click, then you will end up dragging the waveform around instead. So if I drag this cursor around until I position it about here and here, I can basically read the bitrate of this particular signal, which is 500 kilohertz. And that's because this is 500 kilobits per second, and I'm measuring a single bit. Like, does that make sense? Because I'm not measuring the period of this waveform, I'm just measuring the bitrate. So if I, for example, disable persistence here, and I look at the actual signal, and I single capture it, like here's 1 bit, right? That's actually 1 bit of the signal. And so this is like 0, what is it, like 1110, right? And so is that like 1? No, that's actually just, yeah, so that's 0110, so that's 2 bits right here, so it's 3 bits in this space. And you're trying to get the bit rate, right? So you're trying to get the number of bits per second, not the period of the waveform. So you just measure a single bit, that's all you need to do. And so Mike's Electric stuff made a video like ages ago, I remember, where he offered like an autobaud code for his FPGA that he was working on at the time, which would automatically detect the baud rate of the signal and then lock onto it, and that's how you actually would do that. You just measure the shortest pulse, and that's your bit rate. So it's because an FPGA can sample way faster than this, obviously, right? You can sample at like 200 megahertz on most FPGAs these days, and you can just measure that very easily by sampling multiple times, like measuring the actual transition time and getting a pretty accurate baud rate for your waveform. But you can get it like this as well with cursors. So now that we know what the baud rate of this whole thing is, I'll just disable cursors, and we can try serial decode. So to access serial decoding, I would flip up on the channel menu, and now I have math, reference waveforms, and the 2 serial decoders. By the way, you might be wondering what this level thing is in the middle. So if I just have a regular thing here, and I click on this is actually just trigger level. That's all that this is. And if I pull out on this, then I actually get like a quick trigger menu, which also gives you your oscilloscope mode, including, normal mode, if you know what that is, or auto mode, where you have like forced sampling. Normal, when it only samples on trigger and nothing else, of course. And then you have, do you want to trigger on a rising edge, falling edge, or both? So really cool. And then which channel is being used for triggering. So very, very actually convenient and very fast to access. And here's your actual trigger level, right, which you can set here. And speaking of triggering, you can actually trigger on UART as well. So you can trigger on specific data, for example. So if I go to the trigger menu and I go to S1 UART, I can set a particular trigger word, which in this case is 0A. And look at super stable now. So very, I think, intuitively put together. So if you swipe on the channel menu, you get this stuff, and now I can enable serial decode, and I will pull that out, and right now it's decoding junk. And now, because I need to set the correct bitrate, which is in this case, I go to user defined, and I enter 500 kilobits per second, and now I should get a valid decode. So, but I need to, set ASCII. There we go. So now if I do this and I just single shot, you can see it says Micsig with 2 mystery characters and then more Micsig. And of course, one of the things that you can do is you can, let's say, reduce the time base quite a bit, single shot, right? And then you have a zoom function. You can click on zoom, and now I can zoom into this particular thing, and I can move the zoom window around either with this control, or I can just move it manually over here. And of course, I can change the zoom level, so I can zoom in, you know, further. And this is really useful for looking at very long waveforms, right? So if you have like a very long waveform here and you want to examine it in detail over time like that, then the zoom function is really good. You click on it and it goes away. Very cool. So it makes it quite easy to scroll through these long waveforms. Back to serial decoding. So let's say I want to see what this actually looks like as a page of text, right? So because I have it set to ASCII, I can do that. I can swipe up from the bottom, and I can select this, serials text. And now if I click run, here's the text. So this is actually kind of wonky. It's capturing the frames, which is good, but the text doesn't seem to update super frequently. It's like it updates once in a while, and then it stops updating, and then it fills up its buffer. So I'm not 100% sure what's going on here, but if I stop it, I can scroll through this. I'm not sure how long this buffer is, but certainly it's really easy to scroll through if you just want to see what the text is. Another thing is that it's ignoring the line feed and carriage return symbols, because that's what's actually in between the text. So if I mean, I don't have to clear it, I guess, but if I go here and I switch it to hex instead of ASCII, and then I go back to the serials text window, and then I run the scope again and I pause it, you can kind of see that the two symbols in between the text are 0D and 0A, which is a carriage return and line feed. So for people who don't know what that is, when you press enter on your keyboard, technically it does two things. It returns the cursor to the beginning of the line, and then it moves to the next line, one line down. So the process of returning to the beginning is carriage return, because back in the day you had physical typewriters and teletext machines, which is like, if you want to know more about that, you can watch Mike's, I was going to say Mike's Electric Stuff, Curious Mark, his channel. He makes a lot of videos about those kinds of things, which I don't know much about. But, you know, you had a physical print head that had to return to the beginning position, and then the paper would advance or whatever to print the thing. So the line feed is a paper advancing. And, you know, we're still kind of stuck with these old conventions, but that's what's actually going on when you want to move to the next line in a terminal, you know, or whatever on your computer. So in this case, you need both in order to be able to do that, but Micsig's ASCII display for text seems to be ignoring that. And of course, as another thing, I can't single shot this. So when I click single shot, nothing happens, which is kind of unfortunate. I would have, you know, like this feature to clear this and just do a single acquisition for the length of the waveform, and then just dump me the text from that, right? Because I might want like a single trigger event that I want to trigger on. So instead, what you would have to do is, you can't use this window at all for that, right? You'd have to trigger right here and do your single shot here. So why is that kind of, what just happened? What is this? Why is it shifted? Oh, it's because the trigger point is shifted. So I have to, how do I change that? I have to like click on it. That's the trigger, and then that should shift it. But I did that. I clicked on that. Okay, weird. I'm not sure what happened there. But yeah, I was just at the end of the waveform. So it wasn't a bug or anything, but so anyhow, the point being is that I'd have to single shot it like this, right? And now if I go to that window, I'm going to get nothing. It doesn't decode whatever's on the screen. If I press single shot, it does nothing. So that's kind of unfortunate. I'm not sure how to get around this. I guess you have to basically just look at, and look, when I exit it, what happened? It's like gone. And I can like single shot again. So for example, if I had ASCII set here, right? So right now, and look, I just changed it to ASCII, right? So I go here, I change it to ASCII, this did not update. It's still stuck on hex. So I have to single shot again, then it'll update to ASCII, right? So I can change time base, single shot again. So there's my ASCII. And I can go through it like that. I can use the zoom function to go through it, that's fine. But then if I go to the serials window, I get nothing, and when I leave it, what is that? So little bugs like that, I guess, you know. It's still a product that's pretty new and is being developed. So it's not without its problems. So anyhow, the point is we can display text like that, which is cool, but it's a little intermittent. It seems to kind of not update as frequently as I would like. But this is 500 kilobits. So let's see what happens at other bit rates. So if I go to this whole thing and let's set it to 1, oops, how do you clear backspace? 1 megabit, okay. And now we should get junk, hopefully. And so when we look at, when I set, let me just see here, so I go here, here, set this to hex. Let's look at the serials window, and now we get junk. We get a high error rate, which makes sense. So I guess the yellow characters are the error characters. And because I haven't set the actual FPGA board to output 1 megabit, so now I'll do that, and there we go, it's fixed. And now the errors are going down because the errors form a lower and lower portion of the total buffer, which is being overwritten, right? So when the entire button is buffer is overwritten, the errors will go to 0. But it's like it's decoding, but then it's like not responsive. So I guess you have to wait until it finishes, and then maybe you can go through it like that. And I would have liked an ability to just dump this into a text file. That would have been really good if there was like a save button here somewhere, you know, where I can just save this into a text file on a USB drive, for example, so I can just have this on my computer to be able to display it that way. That would have been kind of cool. But I mean, yeah, I mean, yeah, there's actually no other way to do that, right? Because I mean, you can save the waveform and then decode it manually that way, but who would want to do that? The whole point is you want convenience, right? So that would have been a good feature, to be able to just save this text, or save the hex stuff, or save the text, or both. That'd be nice. So let's go to another baud rate. Let's go to 4 megabit. So let's go back to this window. So we should get junk, which makes sense. And now I'll enable 4 megabit on the FPGA board, and we get good text again. I can clear it. And now I'll switch it to 8. 8 megabit gives us junk again. And I can change the baud rate to 8 megabit, which is the maximum. So if I put in some arbitrarily large number, 56 megabit, it'll just clamp it to 8. So if you ever want to get to 8, you can just put in whatever. And let's see, so yeah, that's all good. And when we run this, and we do serials, we get nothing. So that's kind of a bug that I found. 8 megabit baud rate seems to not work very well for serial decoding. And more to the point, like, so right now I have it stopped, right? I cleared the buffer, I go run, nothing happens. Once in a while, I get like some frames that show up. And to do that, for example, I would have to exit this. Let me run this for a moment. Then I stop it. Then I go to serials, and then I run it. And then they'll show up briefly, but look, it stopped acquiring frames. It just stops. But here it still says it's running. But it's not running. Now it's running. But I go here, nothing. So another glitch, I guess, with 8 megabits specifically. Actually, you know what? Let me just test something out. 1 second. So let's see. If I exit out of this and I adjust the display depth. Okay, first of all, let me see the signal. So let me like zoom in a little bit. So I'll go to sample depth and I'll set it to the lowest. Is that still workable? Yeah, that's still good integrity, so that's fine. I just wonder if the lower sample depth will help it decode faster because it has fewer samples to process. Let's see. No. The answer is no. So not at all. Let me like do what I did before. So I'll just start it, stop it, go back to this window, start it. Oh, now it doesn't even do that. That actually made it worse? Question mark. Let's see. Yeah, that actually, oops, that doesn't work at all. Nothing. Let me like change the time base a little bit just for fun. I mean, it's decoding it just fine here. Go back to serials, run. Nothing. It actually completely refuses to decode this at the lowest memory setting. This is only 7K points. And it's just not doing it. Maybe it's because 7K points is actually somehow insufficient for it. Okay, look, now it worked for a couple of stuff. I mean, it captured a decent buffer in a short time span. Yeah, good luck clicking on this tiny little thing. Like, my god, I need like... my fat fingers can't click on it. Okay, whatever. So, it captured something. And you can take a look at multiple active UARTs at once, or actually both of them. This doesn't make too much sense to me. I think the blue text belongs to channel 1, brown text belongs to channel 2, but I'm not really sure what this is supposed to represent. If you stop this and you scroll around, I mean, like this makes sense, right? Because the signals are exactly the same, they're completely synchronous. So I understand this part, but then what's happening here? Is it just losing sync internally ever so slightly, depending on whatever algorithm it's using to process this? But here we only have the blue channel. Kind of bizarre. But if you have a system where the two signals aren't perfectly synchronous, but maybe one of them talks and the other one talks, then maybe this mode would be useful. Regardless, I think it's still a really good feature to have in a $1,000 oscilloscope. And so this covers the serial decoding portion of it. It works, as you can see, in terms of the types of serial data you can decode. This is just basic UART, and these are the settings you can change for it. There's LIN bus with its settings, CAN bus for cars, SPI for basically everything, I2C. There's 429. This is the ARINC 429 avionics bus, which from my memory uses two differential lines at fairly high voltages for signaling and has these two baud rates. And then there's the Micsig 1553B bus. I actually have one device that will do 429, and I have many devices that will do this. So maybe in a future video I can actually try this out on some real devices that use this particular bus. Congratulations guys, we finally graduated to sine waves. So the reason why I want to show you this is to show you FFT functionality, fast Fourier transform. And I can enable FFT this way by clicking on math, and I'll disable channel 1. And so when I go back to math, I can pull this out to see my settings for math display. So in this case, I've selected FFT as opposed to advanced math, where you can put in expressions and stuff, and double wave, where you do interactions between channels. In this case, I want FFT. And so I select the decibels as the scale. And what just happened? What just happened? I don't know what just happened. Oh, it like rescaled. Okay, that was odd. Oh, I think I understand. Okay, so it when I clicked on that, when I clicked on dB, it reset the scaling for FFT. Okay, now I know. So now I need to basically do this and then zoom in once, and that'll be good. So part of the FFT, there's a trap actually. When you look at the actual channel acquisition parameters, I guess I have to enable it, the default probe attenuation is set to 10x. And every time I reset the scope, it seems to set it to 10x, which will skew all your FFT readings as well as your basic voltage measurements, obviously. So you have to change that to 1x manually to make those accurate, and then it'll work. Incidentally, while we're here, this is where you would set your channel coupling, DC coupling, AC coupling grounded. And you also have a bandwidth filter. You can do a high pass, low pass filter, and you can specify exactly what that filter is. So you can high pass filter the signal, set it to 30 kilohertz, and as I increase the actual signal, hopefully the filtering will be effective, and yet it's somehow not, because I'm in the megahertz range now. Oh, I'm high passing, sorry, what am I doing? There we go, low pass. There we go, now it's gone. Makes sense, right? So you can actually like measure on the FFT exactly, you know, what the filter characteristics would be for this filter. But it seems to have a bunch of harmonics and whatnot, so maybe this is like a digital filter of sorts, which isn't quite perfect. But it's still good enough for a lot of applications. So if I click on full bandwidth, it goes back to normal. But yeah, high pass it, of course, that would allow it to pass through just fine. I build filters, guys, I swear, I promise. So I sometimes know what I'm talking about, but not always. Right, so if we go to this window, I can actually just ramp up the frequency and we can see what we see in the FFT display. So we get a measurement of the frequency. I guess it's like some kind of a peak detection thing, right? So it's, you know, I wish it would put like a little marker on it or something, on whatever it's actually measuring. It'd be nice if it had like a box around it. But it gives you the frequency and it gives you the amplitude. And I don't know what the DC measurement is trying to measure. I mean, is it like power level in relation to DC or something? I mean, yeah, like some weird DC peak here is going down and this is staying the same, so the delta increases, and that's kind of what we see. Is that what's happening? So of course you can use cursors, right? So we can move this cursor around here and we can move, oops, you have to be careful, it's a touchscreen. So yeah, that's about right, I think. Yeah, that's about right. So that seems to be what it's measuring by DC. That was my guess, but I don't know. So you can measure a relative amplitude in decibels, which is great, and you can also measure relative frequency, right? So you can, if you want to zoom in onto an FFT and you want to measure, you know, it's like, well, let's say like, what is the signal level 100 kilohertz from the carrier or something like that, or let's say in this case 1 megahertz from the carrier, and then you can measure what that level is by doing a secondary thing here, right? And you can, oops, unless you touch it wrong, and then you'll get some kind of value for this particular X1, X2 thing, and then you can measure some difference in amplitude from the carrier and, you know, get all your measurements for lightweight RF stuff. I mean, it's only 100 kilohertz. I'm not an RF guy, admittedly. I do high-speed digital, but that's different. So anyways, it's pretty good, right? Like, so see, the joystick is pretty, I clicked on it and it just reset the position. So, you know, touchscreen is kind of better for this. And incidentally, of course, you can click the lock button to lock the touchscreen, so you can't mess anything up. But yeah, so that works pretty well. So I think it's a very good implementation of FFT, considering the price range of this oscilloscope, and it'll be plenty for most things that you're looking to do. It's not perfect. There are obviously oscilloscopes with much better FFT implementations, which almost work as spectrum analyzers, but not quite. Of course, you're never going to get the noise floor that you would get on a spectrum analyzer, but nonetheless, this is pretty decent. And finally, I thought I would mention a couple of extra features for this oscilloscope as far as the front panel buttons go. So there's a quick menu button, which is actually just this bottom menu. So you would access the bottom menu by swiping up, or you can press quick menu to activate it. The main menu is the swipe down menu. So when you swipe down, here's the main menu. And then you have the channel menu. So for whatever channel you currently have selected, when you press menu, you get the channel menu for that, which incidentally has an invert button, which is kind of neat. And you can name the channel, so you can label it, and there's some common labels available, like you can label it data, and so you can kind of see it here, or you can do none. Very convenient and very easy to access with menu if you don't want to do this, because you have to swipe out to get this menu normally. So it's your preference. Do you want to make your screen all fingerprinty, or do you want to press buttons? Up to you. Now I'll briefly show you mouse functionality. So what I'm going to use is a wireless dongle for a mouse. This is the Logitech MX Anywhere 2S mouse. And the neat thing about this mouse is that you can choose up to 3 devices to connect to. The first 2 are Bluetooth devices, and the third is the dongle. So this is the dongle, and I can just plug it into the scope. It'll make a sound, and the scope app will crash. Very cool. Let's try to restart it. Look, it's not perfect. There are some bugs. They're working on it, I swear. Maybe. Okay, so the mouse is not working, and now I can do things like this and, you know, pull things out. And can I do, yeah, I can even pull that out, and I can pull the bottom menu out. So it's potentially easier for some users because you can just click on things to activate whatever instantly. By the way, hold off time, so the setting is definitely there for those that need it. I'm really assuming you guys are, you know, oscilloscope experts here, but you know. Mouse works perfectly well, and this is now wireless, right? So I like this personally, and so you can use the mouse wheel to change time base, which might be, again, very useful for your application. So this menu, you can drag it around and you can just place it wherever you want. And yeah, so you can kind of operate your scope that way as well. Actually, wait, is auto... Oh, it's that auto. Okay, so it's different from... Yeah, this. It's different from that. So this auto is not the same as this auto. So when you enable this, you're not enabling that versus this. You're enabling the automatic. You're enabling this right here. This is what you're enabling. Anyways, I hope this helps. Sorry that it's a bit rambly towards the end of this video, but now you guys know all the things. I definitely plan to make a lot more videos for this channel. I think a lot of them will be very interesting for many people. I think there are a lot of people on YouTube who make content that's very technical and very specific. I'm going to kind of stick to a slightly more general audience, I think. And I mean, personally, I just want to have fun, and I want to make videos that are fun. If I'm taking time away from my work to do this, I want to enjoy it if I can. So yeah, I have a lot of really unique things that I can cover. I have some very unique hardware I can show. This is the first video I've made for YouTube because I figured, well, I just got the scope. No one has really reviewed it in any kind of detail, and I thought I might post it because it might help some people make a purchasing decision. Personally, I think it's great. I don't really care about the little bugs. I can get used to that stuff. I'm sure they'll update you know, the oscilloscope eventually. Speaking of which, actually, a little aside, so you can go to settings for this, right? You can connect to Wi-Fi for the scope, and you can do system upgrade. So once you're connected to Wi-Fi, you can see if there's an update available for the scope.